Hello everyone, my name is Ramakrishna. I'm here to explain about my thesis work along with my thesis partner, Numan Afsar. My thesis is about designing and implementation of the routing module for a transceiver system operating at 3.125 GHz. This thesis work is mainly focused on these following points: the outline of the thesis, the theory and designs, simulations and results based upon this theory, and testing and measurements, and discussions and conclusions. First of all, this is outline. The outline of this thesis is the designing the routing module for the transceiver system. The basic block diagram of the transceiver system is shown here. This particular transceiver system must be able to operate at 3.125 GHz and it must be able to work in ultra wideband. So from this block diagram we have a transmitter, antenna and a receiver and a common routing module. The goals of this particular routing module that are presented here. Every basic transceiver has two modes of operation, transmitting mode and receiving mode. So transmitting mode is from transmitter to the antenna and receiving mode from the antenna to the receiver. So the goals for this routing module here is maximum power transfer in the transmitting mode from transmitter to antenna and maximum power transfer in the reception mode from antenna to the receiver. At the same time, good isolation between the transmitter and receiver in the transmitting mode, a good isolation between antenna and receiver in the reception mode, and a good return loss at the transmitter in transmitting mode and a good return loss at the antenna in reception mode. So we have chosen the two routing modules which are used in the latest transceivers. One is the micro circulator and the second one is the micro RF switch. So this thesis has two parts. Both will work towards the same application operating this transceiver. Part 1 consists micro circulator, part 2 consists the micro RF switch. So part 1 micro circulator. Before I am going to talk about this micro circulator, the theory behind that I will talk about the theory behind the circulator. So the first part of the theory, the material selection that is suitable for design the circulator. We have chosen the ferromagnetic materials. These are called ferrites. These are the typical materials to use to design a circulator. That we have chosen the ferromagnetic materials. These are simply called as ferrites. The structure of voyaging, atrium iron garnet. So one of the ferrite that I have presented here is the atrium iron garnet. The structure is presented here. Its structure is a cubic lattice structure. It has a cube and different sublattices, commonly called as a cubic lattice structure. So the different sublattices is like tetra, the red one you can see this is the tetrahedral sublattices. Octa, octahedral side it has representing the black one. Dodecahedral representing the blue one. Each sublattices is placed with the different ions and the interaction, how the interaction between these ions, how is it possible that you can see covered by O2 minus ions. These O2 minus ions are covered by all these ions and the interaction makes the interaction between those ions possible. Net magnetization. The ions that are placed in the different sublattices have different magnetic moments. Some of them will have parallel magnetic moments and some of them will have anti-parallel magnetic moments. They cancel each other, there comes a net magnetization. In the second part of the theory, I will talk about the operation of the circulator based upon the material that I have selected. First, ferrite region. A ferrite is an intersection of three transmission lines at Y junction. When you have a ferrite disk and three transmission lines, they will meet at one point. It's called the Y junction. This is where the point that the ferrite region occurs. There are basically four types of ferrite regions. The first one is FMR that you can see here, ferromagnetic resonance. The above is the right side and the below resonance is the left side, and the low field loss region is extremely at the left side. Low field loss region. These are the four basic types of ferrite regions. So I have to choose one of the regions to operate the circulator. So let's check where FMR occurs and when the other modes of operation occurs. FMR, ferromagnetic resonance, occurs at omega is equal to omega naught, where omega is the angular velocity of the electromagnetic wave that you apply to the ferrite. Omega naught is the omega naught is the angular velocity of the electrons that are placed around the magnet, which is placed inside the ferrite. So when these frequencies are matched and when they are in the same direction, this ferromagnetic resonance occurs. So operation at ferromagnetic resonance and low field loss region. Operation at this resonance, ferromagnetic resonance, and this region gives more losses. When you apply a certain magnetic field on normal to the ferrite, you can see in the graph. This is the graph gives information about the resonance curve of the ferrite material. The losses in this region and this region, when you apply certain magnetic field, are high at FMR and also high at low field loss region. So these two regions are related due to this region. We have more losses. It will gives a bad circulation in the circulator operation. So below and above resonance regions to operate. So we have eliminated two regions. We still have two more regions to operate the circulator. We have to choose one of those which is suitable at this operating frequency range. So before we are going to select those two regions, we have to know a brief idea about the standing wave pattern. How does it works when you apply a signal to the ferrite in presence of magnetic field and without presence of magnetic field. In presence here and without presence here. First, a signal applied to the ferrite at port 1 will be divided into two equally circularly polarized waves with the same velocity. One will reach to port 3, that will be coupled, another will reach to port 2, that will also be coupled. This is the case when there is no magnetization normal to the ferrite. When you apply some power or when you apply some signal, it will be divided into equal and it will be one transfer to the port 2 and half part will transfer to port 3 and half part will transfer to port 2. Once you start applying certain magnetic field in the second case, the velocities of these two circularly polarized waves will not be same anymore. One of the wave will come in phase to the other wave and both will be coupled at one port and both will be cancelled at the other port. So the circulation occurs in a clockwise direction, and so if you start applying a certain magnetic field at this operating frequency range, if you start applying even more magnetic field, that considers in the third case. In that case, the wave starts rotating in anti-clockwise, and this will be opposite. Like port 3 will be isolated, and port 2 will be coupled. All the power that you insert at port 1 will be received at port 2, and port 3 will be isolated. So this is the basic standing wave pattern. Now we will choose which mode of operation is suitable. Lower magnetic field biasing used in below resonance mode. This is the case that represents the below resonance mode. So at this operating frequency, we must use a lower magnetic biasing field. If you use a lower magnetic biasing at this operating frequency in below resonance mode, the ferrite won't be able to saturate in excess, and it will still remain some kind of magnetic losses. So it will give a more losses in the end of the circulator operation, and it will result a bad circulation. And at the same time, higher magnetic biasing field used in the above resonance mode. This is the third case. At this operating frequency range 3.15 GHz, a higher magnetic field biasing that we have to use in the above resonance mode of operation. This will saturate the ferrite in excess and optimizes all the magnetic losses and gives a good insertion loss and gives a good circulation at the end. So we have proceeded to operate the circulator in the above resonance mode due to this reason. So in the third part of the theory, then I will discuss about the design of the circulator. This is the basic design that you can see here. It has the two ferrite discs and the microstrip center connector, and these are the transmission lines. And this is the magnetic field that I have applied normal to the ferrite. So first, the power transfer in circulator. Since we have chosen the above resonance mode of operation, how does this power transfer in circulator occurs? The power that you insert at port 1 will be received at port 3, and port 2 will be isolated. This is the transmission mode, and the power at The power inserted at port 3 that will be received at port 2, and port 1 will be isolated, and this is the reception mode. This is how the power transfer in circulation occurs in thermoresonance mode. So differential line technology. There are two transmission lines here that you can see. This is the differential line technology in the microstrip line. This contains three conductor system. This is called the three conductor system, which has two signal traces that you can see here, 1 and 2, and a ground plane. At the bottom, you will have a ground plane. Here, the voltage difference is the signal traces. Voltage difference of the signal traces. Here, the signal is nothing but this voltage difference between these two signal traces and zero ground current. The current between these two lines is very high, and at the end of the receiver or at the other end, it will be coupled each other. They will add each other, and when you compare to the ground current, it will be very high. So the ground current is assumed to be zero. Due to this coupling, less electrical interference and high transmission rate we can achieve. These two lines are arranged very close to each other, and when you are designing, and they produce coupling in the end of the receiver, and due to that reason, we can have less electrical interference and high transmission rate. This is the simulation model according to the theory. According to the theoretical design that I have shown before. This design has designed in using HFSS simulation software with a finite element method. According to the same theoretical design, you can see the two Faradays and the transmission lines with two lines, differential lines. So boundaries and excitations are applied to this microstrip lines, and two Faradays that I have used here, and also microstrip conductor lines are used in between them. And all these microstrip lines are designed on a FR4 substrate, and all this whole setup is enclosed in a casing called a brass casing that you can see here in the hexagonal brass casing. So this is the basic simulation model that I have designed. This is the basic routing module that I have designed, and now I will talk about the results of this design. How does it work? So here is the results part. In the results part, if we talk about the S parameters, the results part. S31 insertion loss. The blue line here gives information about the S31. S11 return loss. The red line will give the information about the return loss. S21 isolation. The gray line gives information about the isolation. All these are the levels of this insertion loss, return loss, and the isolation at operating frequency. We have minus 0.2 dB insertion loss at operating frequency, something like 3.125, and 15 dB of insertion loss at operating frequency, and 12 dB isolation at the operating frequency. Poor bandwidth 5%. Yes, this is a very poor bandwidth. If you can see, from 5% is nothing but maybe 150 megahertz. When you consider this operating frequency, it has a very poor bandwidth. The upper cutoff that you can choose is from somewhere over here, like 3.1 or 3.2, and for these three S parameters, so it will be like 5% of this operating frequency. So every design, these are the results that we have obtained is not enough for this application-based communication application. Those S parameters are not enough. So every design can be implemented or can be tuned or can be optimized using certain parameters which are suitable to optimize, which are suitable to tune. So in this design, I have choose two parameters. They are really suitable to optimize. One is the microstrip widths, and the second one is the externally applied magnetic field normal to the ferrite. The first step of optimization is continued with the optimization with different microstrip width from 0.05 millimeter to 0.25 millimeter. In step response of 0.05 millimeter. So it will be totally 5 steps in between these 0.05 to 0.25. So this graph gives the information only about this insertion loss in the optimization process, first step of optimization process. S31 insertion loss. All these 5 steps, all these 5 lines, they give the information about curves, give the information about this insertion loss. Minus 0.1 dB insertion loss at the operating frequency 3.125 GHz. The insertion loss level is minus 0.1 dB. You can check this blue line. Blue line at this operating frequency range. This is the minus 0.18 dB. And also in the point of bandwidth, from upper cutoff is at 3.4 gigahertz, somewhere over here, 3.4 gigahertz, and the lower cutoff is 2.9 gigahertz that are considered here. It covers a minus 0.2 dB insertion loss between this bandwidth. Between this band, it's like 2.9 to 3.4. It's like 500 megahertz. 500 megahertz is the 15% bandwidth of the operating frequency, 3.125 gigahertz. That this is the 15% that we have achieved from 5% to 15% insertion loss with the first step of optimization.